Good evening, boys and girls. Welcome back. Today we're going to jump right back into talking about the heart, specifically the cardiac cycle. Here in front of me, this handy dandy drawing is what I call the pressure volume loop. This is a very simplified illustration of the way that our heart pumps blood. If we're thinking about the left ventricle specifically, this is what's going on every time blood comes into your heart organ and pumps it back into the rest of your body following its oxygenation. So, what these axes represent are pressure and volume, P and V, and what we see here is an enclosed loop. D represents the end diastolic volume of your ventricle, meaning this is what basically the max volume of that uh, valve looks like before the contraction is initiated. And the volume of blood that we see just before that contraction happens is what we call the preload. Right before all of that blood is forced out, we have this max volume. It's like that tipping point right before all of that blood is forced out into the body through the arteries. And so we continue up the loop to reach our afterload. And what you'll notice between afterload and preload is that there's pretty much a straight line going up between them. That's what makes it an isovolumic contraction, meaning that the volume does not change. Our end diastolic volume stays right where it's at until the semilunar valve closes and the volume of our left ventricle decreases until we reach our systole, meaning when the opening starts to shrink. And this is when relaxation happens. So we have our preload and our afterload, and the pressure is pretty high at this point. This is when all of the blood is being forced out at a yet another isovolumic uh, amount of blood. So we are at a lower volume, but it remains consistent as the valve relaxes. Now we also have an arrow here representing our inotropy. You might remember talking a little bit about inotropy and chronotropy in the previous video. Well, this line, our inotropic line, essentially just represents the stiffness of the valve that we're concerned with. So right at the top of our end systolic volume during this isovolumic relaxation, if our line is very um, steep, if we have a very steep slope and our pressure is very high relative to our volume, that's going to mean that our valve, our our whole loop, contraction and relaxation, it's going to be relatively stiff. You can imagine if you have a very small valve with a lot of pressure built up inside of it, then it's going to be stiff and your heart's going to be working quite a bit harder. If we were to move this entire loop maybe up the x-axis and our inotropic line would fall to a slope closer to looking like this, our volume would become bigger, larger relative to our pressure, and our triangle would look more like this. And intuitively, you can figure if we have more volume relative to our, maybe if I draw the line, like this. If we have little pressure, this is easier to visualize, in a wide volume, a large volume, then our heart isn't working as hard. Maybe we're in a more relaxed state, either due to our parasympathetic system or our beta 1 receptors are being induced by a certain drug. So, moving forward, having discussed our pressure volume loop, I'm going to lead you to this illustration of the heart here, and it serves our needs for now. So here we have our right and our left side of the heart, the left ventricle, as we were just talking about, that pumps all of the oxygenated blood to the body through the arteries, specifically through the abdominal aorta. And here's uh, our thoracic aorta and all of its branches coming off of it, right off of the heart here. As blood is being pumped out of the heart upon being oxygenated, it will bounce off of these walls and it will build up pressure inside of this kink, inside of this curve before the aorta goes down to the rest of the body. As those walls are being stretched from the outgoing blood in the aorta, there will be certain receptors called baroreceptors. If you think of a barometer, these are receptors that are sensitive to and measuring pressure. They are being inflated by this incoming blood, similar to a water balloon. So off of these initial two branches, I believe it's brachial branch. Don't quote me on that. But the point is, we have baroreceptors in these chambers coming off of the aorta, and these have synapses and neurons that connect all the way back to the brainstem. And these communicate with our hindbrain how much blood is being pumped out of our heart and how hard it's being pumped out at any given moment. And if the baroreceptors are detecting a certain pressure that is a lot higher than we are acclimated to, it's going to signal perhaps the parasympathetic nervous system in our brainstem and say, whoa, you need to slow down, Buster. That's too much pressure. We're going to go into cardiac arrest or something. Or perhaps if the baroreceptors are picking up very mellow, very slow rates of blood being pumped out, our sympathetic nervous system will be activated. That's our fight or flight response. And our brainstem will send electrical signals telling the heart that it needs to speed up a bit. Maybe if you are going into shock, if you're losing a lot of blood and your heart is starting to slow down because there isn't as much blood to pump, your brain will try to accommodate for that and tell it to pump more blood. But you can see how that would be a problem because there isn't always going to be blood there to pump if you're suffering from massive injury. And that's why it's so important that we maintain homeostasis in our body and why we take care of ourselves. If we're suffering from an injury and we're hemorrhaging blood, we need to bandage that up very quickly because our heart is only going to start beating even faster thanks to our baroreceptors here. Our heart is operating under the assumption that blood will never leave our body. But that's why the clotting cascade is important. So moving on, all of these sort of variables that we're talking about with baroreceptors, and I should also probably explain a little bit about what chemoreceptors are. You can find them in similar locations as the baroreceptors and also just throughout the circulatory system. The chemoreceptors that we use the most are the kind that detect the levels of carbon dioxide in our blood. An example of the way these work is if you aren't getting enough air and there's sort of this buildup of CO2 that is suffocating your cells, then your heart will beat faster in an attempt to compensate for it to get more oxygen flowing. So we see our stroke volume increasing, we see our heart rate increasing. There's a couple of more variables on top of these that contribute to and regulate mean arterial pressure, which is essentially just the measurement of in any given artery, uh, how hard is the blood being pumped going to be pushing on those walls, forcing them out, and causing a sort of turgor. There's also viscosity that we need to consider. If your blood is becoming uh, thick for some unknown reason, or even if it's becoming thinner than usual due to uh, maybe you're taking a certain blood thinner drug so that it can be pumped easier throughout the body. That's a very common medicine to use for people with heart problems. There's also the length that the blood needs to travel that contributes to mean arterial pressure. The farther that blood travels, perhaps all the way down to your feet, the lower that pressure is going to be, as opposed to coming straight out of the heart. You got to think about the inertia. Like if you throw a baseball, the moment that baseball is coming out of your hand it has all of that force behind it. It's going to be traveling a lot faster than if you check on that ball again in 2 or 3 seconds because of uh, air resistance and loss of energy. And it's a similar concept to this blood being pumped out. And then there's also vasoconstriction. If you have your parasympathetic nervous system uh, going on sort of a runaway direction, your vasoconstriction is going to be lessened. You want to be vasodilated so your blood can travel a lot easier, unrestricted throughout your body. Because the classic example of running away from a bear, you don't want your cells to be starved of oxygen. You want to be able to be firing on all cylinders. And those are essentially all the variables that go into mean arterial pressure. We covered baroreceptors, which measure pressure, chemoreceptors, which the ones we're chiefly concerned with, which measure carbon dioxide levels, heart rate that contributes to arterial pressure intuitively because the harder your heart is beating, the faster it's beating, the more pressure is going to build up in those blood vessels. Your stroke volume, larger volume of blood equals more blood pushing against the walls of those vessels. The higher the viscosity of your blood is, the harder your heart needs to work to pump it throughout the body. The farther the length, the harder the heart also needs to work. And then there's vasoconstriction. If you're, for whatever reason, your blood vessels are constricted, maybe if you're experiencing hypothermia, the cold is causing your blood vessels to constrict, your blood is going to need to be pumped all that much harder in order to get to your toes. And that's why your extremities, like your digits on your hands and feet, are the first to turn black and freeze off when you experience frostbite. So going off of that fun visual, I'm going to explain a little bit about the mechanisms by which fluids move in and out of capillaries. Capillaries, as you might understand, are the smallest blood vessels in the body. We have our arteries coming off of our aorta, actually. Let's say this is your coming off of your femoral artery and going all the way down to your feet and your toes. You have sort of like a plantar artery in your foot, I believe. And these arteries form sort of a mesh or a network of capillaries that are so thin that they are about the same diameter as a single erythrocyte or red blood cell, which I found really interesting. So we have this tiny tube of endothelial cells that's just barely big enough to fit individual red blood cells through. And as these red blood cells, like inner tubes, are being squished and squeezed and being forced through in a single file line, it's a lot easier for things like oxygen and nutrients and H2O to diffuse through this very thin layer of endothelial cells that we see forming the walls of our little capillary tube. But what are the forces that actually cause these fluids to move out of the capillaries? Well, I'm glad you asked. We're going to start by talking about something called hydrostatic pressure. We talked about how stroke volume and heart rate can increase the pressure that the walls of the aorta experiences as the blood is coming out of the left ventricle of the heart. Or this is actually, this is the atrium and the ventricle here, correct? So it's very much the same concept as blood travels through the capillaries. The more blood that is being forced through, the more liquid that is causing turgor in these capillaries, the more hydrostatic pressure we experience. We experience. And that is a force that brings fluid out of the capillaries. If you think of a very full water balloon and you poke a hole in it, obviously water is going to start streaming right out because the pressure on the walls is high enough. Whereas if a water balloon is only half or a quarter full, you're not going to see as much water coming out. It's going to be reduced to a dribble. Now, these little squiggly lines that I drew both inside and outside of the capillaries represent proteins, essentially. The proteins that we're most concerned with are inside of the capillaries, and these this is mostly albumin, I believe, like up to 80% or thereabouts. And these are colloids. Colloids are particles in chemistry that do not settle with time. If you think of a snow globe, if you shake it up, if you wait long enough, all of the snowflakes will settle at the bottom of that snow globe. That's how you know the snowflakes are not colloids. Colloids are different because their density, their mass is actually so low that they are unaffected by gravity. As a function of time, these will never settle at the bottom. They will just continue floating through what, in this case, the liquid that they are found inside of. So our albumin here, just going to double check. Yes, albumin or fibrinogen built up inside of this capillary are colloids. And we also have colloids on the outside of our capillaries here. And these create a chemical gradient that can either attract water to the outside or to the inside of the capillary. Our BCOP, or blood colloidal osmotic pressure, is what draws water or fluid into the capillary. Our interstitial colloidal osmotic pressure is what attracts fluid to be pulled out of the capillary. So far we have hydrostatic pressure that forces fluid out, BCOP that pulls fluid in, and ICOP that pulls fluid out. There's actually one more capillary level force that has to do with this little tube that I drew down here, is our interstitial fluid pressure. The more pressure, as the name would suggest, is built up in the interstitial fluid, the more these lymph tubes, the best way I can describe them, are essentially going to vacuum out the lymph and pump them around the body. And this is a part of our immune system, actually. So we have essentially what works as a vacuum tube pulling the fluid away from the environs of the capillary. So that would naturally work as a force that pulls fluid out in either a direct or indirect way. So we have our three forces that are pulling or pushing the fluid out of the capillary, and our one force, our BCOP, pulling the fluid in. So naturally, at least on the arterial side, we have these three forces pushing fluid out of the capillary. It's going to, by default, we're going to see a gradient that sees a net pressure forcing the fluid outside by a measurement of 13 millimeters per 13 millimeters of mercury, or mmHg. But on the venous side of the capillaries, however, we've basically exhausted our ability to force all these nutrients, all of this oxygen, all this water to be diffused out. And uh, the gradient shifts actually to a measurement of 7 millimeters of mercury, mmHg, pulling fluid into the capillaries. And if you're thinking about this in terms of just the way that the heart circulates blood through the body, it would make sense. You have this very nutrient, oxygen rich blood with uh, basically just train cars full of goodies for the cells surrounding your capillaries, even down to your toes. All of it's being dumped out, and you have these empty train car buckets, and there's really nothing left to do but to fill them back up. And this is where the waste from your cells is drawn back into the capillaries, or the venules more like, before it's taken back up to the blood. And so we have, again, our nutrients being dumped out, our waste being taken back in and back up through the body until we eventually reach that right side of the heart again. So the last topic that I'd like to cover tonight is edema or swelling. If you've ever had a bruise or uh, were allergic to bees and got stung and underwent anaphylaxis, those are examples of edema. And I want to go over an example of those real quick, of how edema works, at least on a capillary level, you all. So here we have our vena cava on the right side of the heart that brings the deoxygenated blood back up to be circulated upon having all of its goodies dumped into the cells surrounding your capillaries. But what happens if you're experiencing right-sided heart failure? If there's, for example, a scarcity of blood being pumped, so your heart needs to work harder, and it starts kind of a positive feedback loop where due to your heart having to work harder to pump the blood, your almost said cell walls, the myocardium, the muscular walls of your heart get thicker, and so your ventricles decrease in volume, and it just keeps getting smaller and smaller Well, if your myocardium gets thick enough and you can't pump as much of a volume of blood as you're used to, your blood is going to slowly get backed up. You're going to have all of these are blood cells, backed up, waiting their turn to get pumped into that right atrium and then ventricle and into the lungs to be oxygenated again. If it gets bad enough to the point where your blood cells are going all the way back down your venous network, and I really hope this hasn't happened to you before, down to a capillary level, your blood cells are eventually going to be squeezed, or all of the fluid rather, alongside your blood cells, all the interstitial fluid, there's going to be no more room for it. It's all going to be forced out between these endothelial cells of the capillary walls. And that doesn't bode well for the rest of your bodily system, because if all of your interstitial fluid is being squeezed out of these capillaries, it's going to be competing for space with these cells. And this typically is most visible, most noticeable first in your abdomen and also in your feet, because these are soft tissues and they're also uh, relatively far from your heart, respectively. And so you're going to see swelling in your feet, just big, mushy masses, also in your stomach, because that interstitial fluid is being forced out of the capillaries. And even though these capillaries are small, they make up a massive network spanning all across your body. Every area of your body has capillaries in it because your oxygen needs to diffuse at a cellular level along with the nutrients and the H2O. So that was one example of edema and how it's caused, along with our variables, our factors that contribute to mean arterial pressure. And we also talked about inotropy and our pressure volume loop. And I hope these explanations were succinct and clear enough to understand. And I hope it was uplifting for all of you back home who were able to watch. Thanks for tuning in again, and I will see you next week.